All right, cool, cool. Um, we're live. Cool. I'm actually recording it this time today, so I'm going to post this up on YouTube or whatever afterwards. Um, so I'm going to try to talk a little bit more about what I'm doing. It's still not going to be like a tutorial or a lesson or anything like that, but here's my cat. Make sure you guys know that I've got my cat going. So yeah, I thought it would be kind of fun to try to record myself just making a very, very simple little Game Boy game in assembly language. I thought it would be something that maybe some people would find interesting. I don't know. So the game I'm making is Breakout, classic game with a paddle and a ball that you're breaking all the bricks, also known as Arkanoid. And we're just going to see how that goes. It's a pretty straightforward game. I don't want to make any predictions. I don't see this taking more than like a couple of months tops of daily 1 hour work. I'm pretty familiar with the Game Boy hardware, so hopefully nothing too unexpected will come up. So yesterday I basically just got the system booting. Nothing exciting happens. We clear the screen. Hey Nelly. We clear the screen and sort of turn it off, turn it back on. We've got the vertical blank interrupt set up. That's just code that gets run once every 60th of a second, so you kind of use it to keep the timing synced, and it gives you an opportunity to update the screen memory. While the screen is being drawn, the screen memory is locked. You can't touch it from the CPU. So once it's finished drawing, this interrupt code fires vblank, and that gives you an opportunity to update your screen data. So generally what you do is you kind of run all of your logic while the screen's being drawn, and then you get a brief window of time to update the screen in accordance with what's changed in the game state. And when I say brief, I mean like really, really brief, like 4,000 cycles or something like that, something insanely small like that. So the vblank code needs to be really, really small and really, really fast. And right now the only thing we're doing in vblank is we save all the current data, the current CPU state into memory on the stack, and then restore it at the end, because this can just get called wherever and we don't want it to mess up what we're in the middle of doing. And then we invoke this DMA, direct memory access code, and what that does is that's like some specialized hardware on the Game Boy which lets you update the state of the sprite registers, or not registers, but the Game Boy has special hardware support for sprites. Let's pop this open so you can see. It's got 40 slots for sprites, and each of those slots is 4 bytes long and contains like what's the X location, what's the Y location, what tile to use for the sprite. So that's called OAM, object something memory. I'm not actually sure what the A stands for. Anywho, so it provides some specialized hardware which lets you write that very, very quickly every frame. So we need to invoke that, and that code actually needs to get run from memory. So you need to copy the code into memory, which we also did over here. You need to copy that code into memory because while it's running, the CPU can't access the cartridge. It can't access main memory, so it actually needs to run from a specialized chunk of memory called high memory because it's really, really high in the address space. the CPU is locked out of that, but it continues running while the DMA goes. So what you need to do is you kick off the DMA process by writing to a special register, and then while it's happening, you just basically need to idle because you can't do anything. Memory is completely locked from the CPU. So if you try to just run any code off of the cartridge or any other code, any code that's not in high memory, you'll just get garbage back and your program will crash. So that is the stuff that we did yesterday. Enabled the interrupts, set the screen up, did the shadow OAM. Oh, and we also, this is just defined some header information. Most of this stuff is not actually used by the Game Boy. It's just Nintendo required it on the original cartridges for whatever reason. And so to make our game more like a legitimate cartridge, and also to make it easier for emulators use this information to sort of configure exactly like what the cartridge was like, how many ROM, how many bytes of ROM were there, how much RAM was there in the cartridge. In order to configure that, emulators often look at this. So having it there is generally a good practice. So today what I wanted to do was try to get sprites working. Like in particular, I want to get a ball bouncing around, and depending on how much time that takes, I want to maybe even get a paddle going. Well, that's like a stretch goal. That's probably not going to happen. I only want to do this for about 90 minutes. So I'm going to try to have a ball going. Let's get started. What should we start with? I guess let's define the tile data. I'm just going to do everything right in the file, and then later on, maybe I'll try to refactor a little bit and move stuff into separate modules when it starts getting a little unwieldy. Tile data. We're not using any sort of fancy memory mapper or anything like that, so just 32K of flat memory. That should be enough for breakout. Makes things a lot simpler. If we start to run out of space, we'll switch to using a memory mapper and try to work all that out. But that's a real pain in the butt. One of the more unpleasant things about Game Boy coding. So I'm going to try to avoid that if possible. And for this, just because the graphics are really simple and we don't need a lot of them right now, I am going to actually just use, like, instead of drawing the graphics in another program and writing a converter or using a converter to convert like a ping file or whatever bitmap file into proper Game Boy format, because they're so simple, I'm just going to actually define it inline using constant data. Yes, Nelly, hello. Oh, that's cool. I'm actually using a newer version of RGBDS than I'm accustomed to, the assembler that I'm using. And they've added lots of really neat features. Like this wasn't around in the old version that I've been using, so it's neat. But it does have a particular, I'm just trying to find it. It's got a particular format for defining graphics data, which is really, really helpful. Where is... Yeah, that's what it is. It uses that. Yeah, here we go. That's the format. So I'm just gonna draw it using that. So the Game Boy graphics format is kind of strange. So for an 8x8 tile, um, it is 2 bits per pixel. So if it's a row is 8 pixels across, that means it's 16 bits, which means it's 2 bytes. So we define a word for each row. And luckily, the assembler sort of handles the ugliness of how it's set up. It's actually done as bit planes. So it is you define the first bit of each pixel, that's the first byte, and then the second bit of each pixel is the second byte, rather than like packing the bits together for each pixel. It's pretty strange if you're not accustomed to it. The assembler handles this for us with this very useful syntax. So we're just going to draw it by pixel. And I mean, I don't know, it's a ball. I'm not going to... I don't know. I'm just kind of like trying to visualize how this will look in my head. I don't really know. Okay, I guess this actually... You know, it doesn't need to be perfect. I just want some approximation of roundness, you know? It's probably going to end up coming out looking more like a diamond or something. Really, you know, not super important. Should just mirror that. You know, maybe if we're working on this and it turns out to like be the most incredible breakout game of all time, then it probably should have always been in its own section rather than just sitting with the v-blank handler. Not that it really matters. Then, you know, we can go back and we can like polish the graphics. But for now, in the meantime, just popping open a terminal at the moment to use Git for source control. There. Because, yeah, that probably should have always been. Anyways, I'll patch that in later. Not important. So, okay, so we got our tile data. Let's just... stick that here. So we're just going to stick that right in the first tile slot. I don't know if my microphone picked up my cat howling, but good stuff. She just does that sometimes. She's a very vocal cat. Oh, actually, I prefer using D as the destination just because, you know, D are the first letters of destination. That doesn't really matter. 16 bytes. We're going to grab the byte. We're going to copy it in. As a minor optimization, we only ever need to increment E because 16 bytes from 80 6,000 or from 8,000, like we're never going to be wrapping the high byte, so whatever. Let's save. I think it saves 4 cycles. And I forgot to decrim B. Okay. Let's see how well that worked. Oh, did I actually call it? I did call it good. Okay. Let's see. Oh, actually, we don't want to do this. We need, like I said, we need to do it when the screen is off. So let's do it while the screen is off. Cool. Thank you, Windows. Windows just letting me know that I don't have any viruses. Okay, recompile and pop open BGB. Let's open up the debugger. Let's reload my ROM. Let's hit run. Let's see how it looks. Yeah, there's my ball. Hey, that doesn't actually look that bad, which is pretty good for something I just drew. I mean, it's a circle, so whatever. It doesn't look bad, anyways. So that's cool. So I'm just gonna save that. Okay, actually, give me 1 second. I'm pretty weird about my making sure my Git history looks just like really, really nice and clean to kind of a ridiculous extent, which is dumb. So I don't want this. Ooh, that's cool. I didn't realize I could do that. I don't want like the new section I created for the OAM DMA code to be. Oh no, I don't want to pick that. As part of the commit where I am configuring my sprites or copying my sprite tile data in. So I'm just going to go back in my history and edit that. Section. Cool. So we're going to patch that in my history, and I'm going to pop my stash. And probably want to accept both changes, right? And whatever. Get things looking good. Okay, there we go. Yep, cool. So there's our commit. We're going to cool. Next, let's configure our first sprite to use it. It's actually, well, I'm thinking I want to split this init screen up from like turn screen off, clear, split this up into multiple things, but so that way the init screen function or procedure doesn't have like all the ball configuration stuff, but Let's do that. I'm gonna grab it with these guys. VRAM. Come over here. For simplicity's sake, turn on screen, turn off screen, turn on screen. Turn on screen. There's probably a fast way to get it so I can tab everything over the way I want it to, but oh well. So instead of like one big init screen thing, splitting it up is a little bit cleaner. Let's okay. Just make sure that I didn't mess anything up. Still looks good. Everything looks good. Cool. All right. So I think that's all just one nice clean change. I'm not going to go back and try to patch that up. I'm just going to have like a refactor commit there. I probably should have given it a more detailed description, but whatever. Okay, so next what we're going to do is we're going to allocate some just some like information about the ball. And right now, so in the future, we're probably going to want to store some like more precise data about the ball's position, like just the X and the Y. Isn't going to give us in as like pixels, isn't going to give us enough precision. We're going to want to store subpixels. But for now, this is probably fine. I'm just going to do all the initialization with the screen off. It's probably a better way to do it. So init ball. Just put the, I don't want to actually put the ball at 0, 0. Let's put the ball at like 128, 128. Then what we're going to do is we're going to we're just every frame going to write the ball's position into we call it the shadow OAM. I mentioned earlier that we sort of do this DMA copy into OAM memory, so we do that from a thing called shadow OAM. So ball, I'm going to call it setup ball OAM is what I call it. So I'm just going to do it into the first slot of shadow OAM. So let me actually pull up the documentation on OAM memory, because the format is, I don't think it should be too much of a problem, but I know it's not like 100% straightforward, so I'm going to just have it as a reference here. Let's see, where are we? Yeah, here we go. So byte 0 is Y, byte 1 is X, byte 2 is the tile, and then you've got all of these sort of attributes, which I'm not going to be using any of that. So it should be pretty easy. Let's get the Y first. Copy that in, and then we get the X, and then I'm going to copy that in. And we're just going to do this every frame. So all we have to do is update these two memory locations, and then it'll automatically get repositioned on the next frame. So how's that? Okay, it compiles, good, or builds, I should say. It's not a compiler, it's an assembler. Yeah, and there we go. There's the ball. Although, no, I didn't set up the palette, so it doesn't look exactly like how I want it to look. But so we should probably do that. But yeah, there it is. And the reason why it's not exactly centered, well, it wouldn't be centered anyways because 128, 128 isn't the center of the Game Boy screen. The center of the Game Boy screen is what's 160 pixels across and 144 pixels vertically. So the center of the screen is actually at like 80, 72. But then also on top of that, the actual location is adjusted based on the OAM. It's like if you put in 80 in the OAM, it'll actually show up at 64 for the Y position and at 72 for the X position. And that gives you the ability to kind of push the sprite off screen a little bit. So let's see. Haven't done that. Let me just save that now. I'm going to commit. The next thing we're going to do is I'm going to set up the palette, because right now, if we go look, yeah, the object palettes are all black, and that's why, even though it looks like this in memory, like when it's actually showing up there, it doesn't look so great. It looks kind of just solid black. There's no shading, so there's no palette. So let's get the palette going. So the palettes are stored in a couple of registers here. Yeah, so we're just going to want to set this. And the palette is just a single byte, and that's the byte format. Let's see. I'm going to stick it here. Wherever. Eventually I'm going to need to clean this file up. It's starting to get kind of unwieldy. But for now, whatever. So what do we want? I think I set it up so yeah, 3 is black and then 0 is white. So from top to bottom we want 3 is black, 2 is dark gray, 1 is light. Yeah, there we go. That should be right. And if it's not, super easy to fix. Second, I'm so grateful, you know, these days I'm developing on a modern computer where I can like, I don't know, got good source control. Everything's really fast. Can build instantaneously. Test in an emulator. Like, I can't imagine how hard this was to do back in the day, where if you want to test your changes, like you need to flash a new ROM and stuff. probably have to like swap disks to like switch between your editor and your assembler or something horrible like that. So that should do it. Let's see if that worked. Reload ROM. Run. Yeah, look at that. So now we've got some nice shading on there. It's still not like the balliest ball in the world. It still looks kind of more like some kind of diamond, but honestly, it's good enough. So let's save that change. All right, so I guess the next thing we want to do is we want to kind of start to get the ball to move around. So to do that, what I'm going to do is I'm going to ball velocity. Again, in future, possibly even right after I get this working, we're going to want to start using subpixels instead of just raw pixels for these things, because we're not going to get a lot of precision. Like if every frame we're going to start like moving the ball more than like 2 pixels, it's going to start moving really, really fast. We want to be able to move it by like 1.5 pixels or whatever. But for now, let's just set that up. And then I had init ball, and then I'm just going to set the velocities to 1, 1. Run a little procedure called update ball, which is just going to apply those velocities to the position. So to do that, what's the best way to do this? Yeah, it's not super like, it's just, things get kind of dicey once you start trying to do things with like more than one variable. Like, obviously not insurmountably dicey, but just there's a real lack of general purpose registers on the Game Boy CPU, so figuring out exactly the best way to juggle things always kind of like not always straightforward. Like you can't just say like add, like in a high level language you just say like ball x plus equals ball velocity x. But here we need to load the ball velocity, and then I mean we can't even like add, like we can't even do that. Now we need to get the ball x into a register, and then start doing some stuff. I mean, what I like to do is like, right, and we can't even just like do this because like Game Boy doesn't support this operation. Game Boy CPU doesn't support this operation. Like if you want to load from a fixed memory address, you need to do it into A. So like we could put it in B. Like this is the most straightforward way to do this, but this is actually pretty slow and bulky because now we've got this repetition of ball X. So you could start to do things like that. Which is something that I like to do. And then it gets, honestly, sorry. And then what you can do is you can actually get rid of the use of B entirely. Can do this, which I'm a fan of. So now, right now, A contains the ball velocity. you then load HL with the address of the ball X position, and then you can do this to add the ball X position to the ball velocity, and then you do still need to write it back. But I think this is probably the sort of tightest way you can write this code without getting like really fancy. Like you can, I don't actually know if this would help. You could put the ball velocity X right next to the ball X in memory, and then you could avoid needing to sort of have this a big constant address twice. You just like set it once and then increment HL, and that'll point HL to ball X, but it doesn't really matter. This is a pretty reasonable same way to do it. And then similarly, you could try to do something similar with by positioning the X and the Y's together in memory, so you could kind of do it all sequentially. But it's probably not worth sweating that right now. And I do find that like if you start trying to really micro-optimize stuff, you kind of end up going down a real rabbit hole that is probably not worth it. The only place that's really worth it is in your VBlank routine, where things are like really time limited. You only have a couple thousand cycles to do everything, so you want to make everything as tight as possible. And your general game logic code, especially in a game like Breakout, where there's like one moving object, you know, maybe you'll get some power-ups and there'll be a few more, but whatever. I just keep things relatively simple. So that should work okay. Let's see how well, let's see, does that assemble? It assembles. Reload ROM, let's see what happens. Ah, look, and then it moves. And yeah, it's just gonna go off screen and wrap around. Eventually we'll have it like bounce. But that'll do it. So cool. Yeah, looks like a nice big command. Now the question is, do I want to try doing subpixels stuff first or bouncy stuff first? My feeling is I probably want to do the subpixel stuff first. Problem is the subpixel stuff is harder, and I'll embarrass myself in front of the camera while I try to figure out the best way to do it. So maybe I'll, whatever. Just a fun game development, right? Fun of live game development. So instead of storing just 256, or like 0 to 255 as the ball position, what I actually want to do, well, I'm actually gonna hold off because probably until I get the background in place, actually, because you can start to do some like relatively clever things to make your background position really fast. Yeah. Okay. Let me show you how to do. No. Okay. Let's do the subpixel stuff. Let's do the subpixel stuff. So what I'm going to do for the subpixels is instead of storing the position in just a single byte, and that limits us because that means we can only sort of move one pixel at a time. It means we can only, I mean, that's the real big problem. It's like you could, you really, let me actually show you. Like, suppose, so right now we're moving one pixel at a time, and that's like a good speed for the ball. But let's say we want to speed it up. Like that's generally what you want to do in Breakout. You want to kind of like start speeding it up. So the next possible speed we could have is 2. and 2. Let's assemble that and reload the ROM. And now if we do it to 2, like, that's pretty darn fast. Although actually even that is probably still like acceptable. But probably want the ball to be able to move a little bit faster. If we do it at 3, you know, it's been a long time since I programmed a breakout game. Maybe for breakout, we don't even need to worry about subpixels. It's like, did I reload? Like, is that really? Am I? Like, is that 3? Like, maybe we don't need to worry about subpixels. That'd be great. Oh yeah, no, and there's 3. Like, we don't end up actually having a lot of precision here. It's like it goes from like normal speed to fast to really fast. And 4. You know, I'm gonna just try to not do any subpixel stuff. That's cool. That actually makes life a lot easier because it looks like at those 4 different speeds, you kind of like. I mean, it'd be kind of jarring. Like you kind of maybe want to like sort of gradually ramp up between speeds, but I don't know. God. Nah. 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 You do want to be able to sort of like gradually increase the speed. So, you know what? This is educational as much as it is, you know, me trying to build something. So let's do some subpixel work. So the idea is that instead of storing the X, Y position as just the exact pixel the ball's on, you like add some extra memory and you say, okay, we're actually going to store like half pixels. And obviously when you start writing to that to the screen, you do end up just ignoring it. But it lets you do the movement, like the physics, in a more precise manner. And, you know, just makes for better physics. And it makes for like a better playing game because it's not like you bounce the ball once and suddenly it starts going fast, and you bounce the ball again and it starts going really, really fast, and then you bounce the ball again and it starts going crazy speed. Like, this gives you a little more precision. And even if this actually doesn't end up being super useful for breakout, like if you start making another game, it's a really useful technique. Like before I was trying to make a platform game, and like you just need this kind of precision to make a platform game feel good. If you don't have it, your game feels really, really janky because like either the guy is moving super, super fast or he's moving super, super slow, and there's not really anything in between. So what does this mean? This means that when we knit the ball, we're gonna store the Game Boy stores, like in general, when you've got 2 bytes, something that's 2 bytes, it stores the least significant byte first and then the most significant byte first. So we're going to store the subpixels in the first byte and then the pixels in the second byte, so to speak, like the fraction, the decimal point in the first byte. So XORs, I don't know if I mentioned this, it's just like a slightly faster way to set X to 0. When you XOR anything with itself, it ends up being 0. Because if the byte is 0, 0 XOR 0, or the bit is 0, 0 XOR 0 is 0, and if it's 1, 1 XOR 1 is 0. It's the nature of the XOR operation. So this way, this is only 1 byte and 4 cycles, whereas that is 2 bytes and 8 cycles. So just ever so slightly faster. So we're just going to have 0 subpixels right now. And then again, the pixel value we're going to set to 128. Yeah, I mean, you can see there's like a repetitive pattern here between the x and the y, and like it could factor it into a function of some kind, but it's not worth doing. And so then for the velocity, we could just use it, give it the exact same format as the ball position. And maybe that's what I'm going to end up doing. I'm going to just kind of like play this by ear and see how it goes. But it doesn't necessarily make sense to store the velocity in an entire 2 bytes because, like, how fast do we want the ball to go? We don't ever want the ball to move like 256 pixels a frame. So instead what I'm probably going to do is I'm going to store it with like a sort of 4x4 format, where the first 4 bits are pixels it should move for a frame. See, I mean, even that is overkill. Even that is like 16 pixels a frame, which is way too fast. We probably never actually want it going over... I mean, even 8 pixels a frame would be really, really bad. It would make our collision detection really, really janky. Probably we'd start moving through objects because 8 pixels is the size of the ball. But just doing it 4x4 is probably the easiest thing to do. So I think I'm going to store the velocity in this like 4x4 format, where 4 bits is for the pixels and then 4 bits is for the subpixels. So to that end, if we want to keep the velocity as is, what we want is actually we still want 1, right? Because we're gonna, assuming like it's sort of up to me how we want to do it, but like assuming we keep the endianness of like most significant nibble first. To sort of match with the way the pixels are set up in memory. Like these would be the subpixels, least significant nibble first. So these would be the subpixels, and the most significant nibble here, those would be the pixels. So we'll just keep it like that. And then the other thing we need to do, so we're going to start by getting the ball velocity x. So these are the subpixels. And this is where it gets kind of ugly if we have slightly different formats for things. God, maybe we want to keep the same format for things, because otherwise we need to kind of convert. The conversion logic. The conversion logic's probably easy. So right now, yeah, actually, this is fine. So right now we get the velocity, and the first thing we want to do is we're dealing with the subpixels first. So So the first thing we want to do is we want to strip out the pixels from the velocity. So now we've just got the subpixels, and those are in the high nibble. So those are going to be, if we look at this as a byte. So like right now, this means that we want to move by 1 subpixel. Or sorry, it doesn't mean we want to move by 1 subpixel. It means we want to move by like 1 sort of unit of velocity unit of subpixels, which is actually going to be 16 subpixels, and that's what we want. We don't want to be adding it like this, like 1 subpixel, because subpixels are the way this is set up. They're very, very, very small. And there'd be a really big gap, because then the most we could possibly move by in a single frame is 15 subpixels. And that just leaves like this huge gap between the most subpixel movement we can do and the most pixel movement we can do. That's like kind of confusing, but you know, I apologize if you're actually like trying to learn and understand from this. Yeah, just like this is what we want. We want to move by 16 subpixels or 1 velocity unit of subpixels. So all we have to do is use and to take the subpixels and strip out the pixels, and then we've got what we want to increment our subpixel value by. So we're going to do that. We're going to load it in, and then we're going to move over to the most significant byte, the pixels. We're going to have to get the velocity again. And again, this time we're just going to strip out subpixels. Oh, actually, this isn't quite... Well, I'll get to that. Okay. So then the only other thing we need to worry about is if in this addition there's like a wrapping. Like if you know, we increment by like half pixel and then we end up wrapping, we end up like going from 0.5 to 1, like we need to actually increment the pixels. So this is going to set the carry flag if that happens. And what we want to do then in that case is that. So we say here, like, is the carry flag set? If it's not, we skip ahead. But if it is, then we increment. We've moved to the pixel, then we increment the pixel. So like that. So pretty straightforward. So now we just need to duplicate this. Yeah, code duplication sucks, and we could do this with like a macro, or we could write a function or something if we really were inclined. But this is probably fine for now. Like it's like 2 things. Like, the reality is this is assembly language. Like, it's never going to be insanely clean or whatever. At the end of the day, the best thing to do is just comment the shit out of everything and, you know, suck it up. Be a real macho programmer. Wall. we go. Does that build? Apparently that builds, which is awesome. Let's see if it fails terribly. It does fail terribly. So now, here's where things get really fun. Assembly language programming. It's failing terribly. No clue why. I gotta figure it out. So, first thing I'm gonna do is I'm just gonna try to eyeball it, try to sanity check it. So what did we do? We increased x and y to be 2 bytes. You put the subpixels to 0, pixels to 128. Oh, I know what we're doing wrong. I forgot to update the setup all layout. So luckily, this is really easy. We just do the +1 to ignore the subpixels entirely. That's the only change we need to make there, I think. So let's see. Yeah, look at that. Yeah, it's moving at a good solid pace. And now we can try, just as an experiment, we're going to set it to 1.5 pixels. So this will be a little bit faster, but not. Oh, no, I don't want to change it there. I want to change it here. So what I'm instead going to set it to is still 001 for the pixel movement. But then for the subpixel movement, I'm going to set it to, that would be half a pixel. So this is going to be a little bit faster. Shouldn't be terribly, like a terrible amount faster, but just a little bit faster. Yeah, you can see that. It is a little bit faster. And so now we're actually sort of exercising the subpixels code works, because we're actually, affecting the subpixels, doing all that wrapping and stuff like that. So this looks good. Awesome. That wasn't bad at all. Okay. It's been about an hour. I'm going to take a quick break, and then I'm going to, I guess, try to do some kind of like collision detection with the sides. I don't know if I'm going to get that entirely done today, but we can give it a shot. All right, cool. Be back in a second. My very, very cheap BRB. We got our ball moving, and it's moving at 1.5 pixels a second, which is awesome. The next thing we need to do is we need to do something when it hits the side of the screen, so it doesn't just, you can actually see what's happening if we look at the OAN. Like it ends up just going off screen and then wrapping right around. And we obviously don't want that to happen. That's not how breakout works. So what we need to do is we need to detect for when we have hit a side and then bounce. So let's see. Yeah, let's start with detecting it when it hits the right side of the screen. So that's going to be when we update X. What we're going to do here is we're going to say, well, we've got our current pixel position in A right now. I'm going to say go past We'll have to do this again for the left and for the top and the bottom. We'll just start with the right. So we're going to test to see if we've gone past the right side of the screen. So we're going to use the compare instruction. The compare instruction does a subtraction. So we're going to compare to, well, let's start naively. The right side of the screen is at 160 pixels, but this isn't actually what we want to test against, as we'll see soon, but we'll do it here. So it does a subtraction, although it doesn't actually update the contents of the register, but it figuratively sort of does a subtraction. It does like a minus 160 and sets the flags according to that. So if A is 159, we'll do 159 minus 160. We get minus 1, or I mean, we actually get 255 because we're working with sort of unsigned numbers. And like that's going to be a wraparound. It's going to set the flag. So what we do is we do this comparison and we say, well, we're going to go down to here and we're going to give this a label, update line, and we're just going to skip past it. If there's a carry. But if there was no carry, that means that we are at 160 or higher, and that means we have gone past the right side of the screen. So what we actually want to do is a couple of things. The first thing we want to do is we want to push ourselves back on screen. So we're going to set A to actually, let's set the subpixels first. Yeah, we want to get as close to being off screen or on screen as possible without going over. So we're going to set the subpixels to that. So that is like right at the very edge. It's like the 0.999 or whatever. So and then the pixels are going to be 150. And then the next thing we need to do is we need to mirror the velocity so that we start going in the other direction. And to do that, we just negate it. So here's where things are going to start getting really weird, because Game Boy's CPU support for unsigned or for signed numbers is not the hottest. So hopefully everything is just going to kind of work out. We might need to do some weird stuff, is all I'm saying. Some unpleasantness. This might get nasty. This might get nasty. So, like, just as a quick recap, -1 in binary using 2's complement, which is what we're using. That is FF, which makes sense because 0 minus 1 in binary, like you end up wrapping around if you've got a byte, and you end up with FF. So how this works is it's a thing called 2's complement, where like 1 in binary is, of course, just, let's look at the bits, and FF is So you can see all of these bits have flipped. This one hasn't. And what the actual computation is like what you do is you invert all the bits to go from 1 to -1. So you start by and then you add 1. That's how you do negation. So we're going to have to do that. It's just that we're going to need to do that for both the pixel part and the subpixel part. And yeah, things might just get a little bit dicey. I'm concerned about it. I don't know. Let's give it a try. I'm putting this in HL because we are going to need to convert back and forth or write it again. So we're going to get it. And we're probably going to need to read it again as well. Yeah. Right, we're going to need to do sign extension. That's the thing that's going to get nasty. That's all. We need to do some sign extension. And I don't think we're going to need to do any kind of sign extension for the negative. I don't know. I need to sort of see how it goes and think about it. I might even just do that off stream. But let's just start with the pixels. So and pixels are in the lower nibble. So we're then going to, I believe the Game Boy CPU has an instruction called CPL, which is, yeah, that's what we're going to do to just, it's the fastest way to do the bit inversion. This inverts all of the bits. And then that adds 1 to do, that does that negate, choose complement negation that I explained earlier. And then, of course, the problem is we do want to substitute the subpixels back in. Yeah, it's going to get weird. It's going to get weird and fun. I'm just going to put it in B for now, so I'm just going to pour it with a B. Yeah, okay. Okay. Yeah, it's the CPU. It's actually it's people always call it like a Z80 or a GB Z80. It's actually kind of like this weird thing. I think it was made by Sharp, and it's just like a custom core that is actually more similar to an Intel 8080, but the assembly language uses more Z80 syntax, and then it's got like a bunch of instructions that um, neither the 8080 nor the Z80 have. Um, it doesn't have the. I'm not super familiar with the Z80. I know it doesn't have like the shadow registers. It's got much more limited. Yeah, no in out, no exchange, no IX, no IY. Yeah, those are the big things. But on the whole, yeah, there was in the Pandocs a section which compares it to the Z80, but I guess in this version they've stripped that away. I don't know. But yeah, very very similar. Um, just like frustratingly more limited in certain things. Um, Actually, I do think it's a little bit cleaner, right? Because like I know that when you're doing Z80 code, if you want to do like 16-bit math, it's easier to just ignore a lot of the 16-bit functionality and kind of do it manually anyways. Not easier, but it's faster. It doesn't have some of the loop instructions as well as the Z80 has. I think the Z80 doesn't have these bit instructions, right? Um, but yeah, very very similar. Um, okay, so we're just going to do the subpixel reflection now. So what that is we're going to again code a okay, and then here we're going to write back the results. Pixels. So let's see. So I'm just gonna so we'll do that, and then we're just gonna basically do the same sort of thing, inversion, but now because it is the top 4 pixels or bits, we can't just increment A. We actually need to add that to do the negation. I think that should do it. I think it's as simple as that. Of course, now this is really starting to get very, very large and unpleasant to be duplicating it. Oh geez, what did I just do? All right. There we go. Oh well, we don't need to do this for Y yet, anyways. Yeah. Okay. So we don't need to do that for Y yet. It's going to get kind of ugly, so we should probably do some kind of refactor of it sooner rather than later. But let's do that. And then the only other thing now is that we need to what I did there. This stays the same, but now this addition needs to change because now we're working with signed numbers. Yes, I think it needs to change. Maybe it doesn't. Maybe it'll just work. Let's find out. Let's see if it just works. Clearly it doesn't. What did I do? What happened there? I did wrong. Yeah, geez, okay. Yeesh. So we're just like completely jumping out into the unknown. If there's anything that's like obviously busted here. I'm a little surprised this is what we're seeing. I'm actually going to just yeah, if it's that, I'm going to start stepping through this to see where that is breaking. Is that F3? Oh, did I? What? Why is it starting to execute from there? Oh, right. Okay. Because it's position. It's put main inside of just inside of like the header, which is not good. What's the best way to fix this? I mean, this is like inevitably going to be a problem unless I like properly allocate the header. So maybe let me just go do that right now real quick. Cartridge header. Should tell me how many bytes this is. How many bytes is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, so that's 16. So it's 48. Just fill with zeros. Okay, that's part of the title. That's also part of the title. So what happened was it was putting main into the code into the header because I hadn't actually set it up to reserve the header space. And then as part of my make script, we do a little thing which sort of configures the header correctly. It's called RGB fix. It's a program that comes with my assembler, and it was just stomping all over my code. So it's good that we are doing this. Cartridge type, ROM size, RAM size, destination code. Yeah, like what RGB fix does is, aside from stomp all over my code when it's put in the header, like it clears the header out basically, and then it does things like it includes the proper Nintendo logo. The logo that scrolls down when you boot your Game Boy is stored in the header on the cartridge, and That has a couple of purposes. One purpose is that if the cartridge is, contacts are dirty or isn't inserted properly, instead of just trying to run garbage, like it compares the logo on the cartridge to some logo it stores internally, and if they don't match, it freezes. And this also was a copyright protection mechanism that Nintendo did. Their reasoning was that if you are a pirate making a pirate game and you include the Nintendo logo on your cartridge, which would be necessary to get it to boot, you would be like including Nintendo's copyright without permission, and they could sue you for that. And that sort of thing actually didn't end up holding up in court. Sega did something similar on the Genesis, and Accolade, I want to say, included the Sega copyright code on their bootleg cartridges anyways, because they didn't actually have a Sega license. And Sega sued them, and Accolade actually won in court. The judge was like, well, if you need to do this to make your program function, like, you can't copyright it. But we still need to include that ROM data. And then it also does things where it fixes the checksums. Oh. And these checksums aren't actually used. Oh, actually, I take it back. Apparently, the Game Boy does use the header checksum for, otherwise the boot ROM locks up. And then the global checksum isn't used at all, but emulators do use it. They check to make sure that emulators just look at it and yell at you if it's not right. They still work. Anyways, so RGB fix corrects those checksums as well. So that's why we use it, and that's why we can't store program code inside of our header like we wish we could. I'm going to do that. Oh, and I've got an error somewhere. I put ROM instead of ROM 0. There we go. Let's see here. Let's reload the ROM, and hopefully it just works. Doesn't just work. There is some kind of a bug. That's okay, though. Yeah, we probably could have gotten it fixed if I hadn't forgotten to set my header up properly. So, we are at time. We'll just fix this bug tomorrow and get the bounce working properly. Thank you for watching, people who actually came and watched. I'm going to post this on YouTube as well, and I'm going to try to post these videos on YouTube. So if you miss this tomorrow and are inclined to watch, you can catch up on YouTube later. Or if you missed the beginning and are curious about how that went, you can check that on YouTube. Yeah, all right. Thanks very much. Take it easy. Have a good one. Goodbye.